So here we are with a question. A chain of length L is placed on a smooth spherical surface of radius r with one of its ends fixed at the top such that the length of the rope is less than pi r by 2. The length of each element of the chain when the upper end is released is. So one thing which we will notice here is this one. This particularly says that if we see the circumference of a circle is 2 pi r, so the circumference of a semicircle will be pi r and the perimeter of a quadrant will be pi r by 2. So the length of the rope is smaller than this part, so it is not touching the ground here. So here we will see that the chain of length is L, it is given, and it is on a smooth spherical surface of radius r. The acceleration of each element of the chain when the upper end is released is. When there is each element written here, we surely get to understand that we will be using differentiation and integration right here. So let's take small element of the length of the L length of the rope. Let's take a small element, namely x. Therefore, name it. And let the length x subtends a small angle d theta at center of the path. So what I'm saying is that suppose we are taking a very small element of the rope like this, and maybe it is subtending an angle like this. So this small angle I am naming it as d theta. So we know that x by r is equal to d theta. So we can just get a relation between theta and that small element of rope, that is x is equal to r d theta. Now let's assume that the mass of the L rope is uniform. Therefore, the mass per unit length can be as m by L. Therefore, the mass of unit length of the rope is m by L. So the mass of r d theta, that is x, that is a small element of the rope L, will be m by L into r d theta. It's okay. So now we will be looking into another concept in the image. Let's see. Now if you see the diagram properly, then we are finding that there is a semicircle like this, and the rope is given like this. So now if it is a perpendicular with the surface and r, okay, g will be always acting downwards. So here at each point, suppose I am letting only one point not to make the diagram very much congested. Here a g is acting. Now if you will see that when we join these 2 points, we are getting an angle theta. So this will also be theta by alternate interior angles. So the component of g along this will be g sine theta. Okay. So we got the mass of the small length, that is r d theta into m by l, and we got the acceleration of the small element of l rope, that is g sine theta. So multiplying this we will get the force, but this force is what? This force is a force on the small element of the L rope. So it is very small, considering it to be dF is equal to this mass into acceleration. Therefore m by L r d theta into g sine theta. Let us rearrange this equation and write dF is equal to m r g by L sine theta d theta. We are just rearranging to keep the constant on one side and keep the variables on one side. Now integrate this. Into sine theta d theta. Now to make it a definite integral, we have to find the limits out there. So one thing we'll see that it is released from the upper end, means the acceleration just after release, and it is also given the length of the rope is smaller than the perimeter of the quadrant, as I have told earlier. So let's assume that the length is like this and it subtends an angle theta over there. Wait, drawing it here. So just after release means it moves a negligible amount of distance right there. So we can say that when it is not just, it is just moving, it is just starting to move. So the acceleration at that point, so the limit will be taken from this angle and will continue to this angle, that is theta. I hope you understand. So from 0 to theta. Okay, so integrating this we will get f. This is a constant, as we saw. Integrating sine theta will give us minus cos theta. Being a definite integral, we will not add the constant and give the limits, theta on the upper limit and 0 on the lower limit, and we will just put the value of the limits here. So at first we will put 0. No, at first we will put the upper limit minus the lower limit. So minus cos theta minus of minus cos 0. Okay, so we'll get mrg by L 1 minus cos theta. Now this is a force. The whole mass of the rope is m, which we already told. So dividing the force with the mass, total mass, we will get the total acceleration. So when we divide it by mass, divide 1 with mass, we are getting rg by L 1 minus cos theta. We are very close to the answer right now. Now, one concept while we were talking about the limits is it is just moving by an angular distance theta. So how we can represent this theta? If we apply this formula right there, so there theta will be equal to L by R, that is arc length, that is the length of the rope, by the radius of the circular path. So substituting the value of theta in the above equation, we get our answer as acceleration is of each part of the element is r g by L 1 minus cos L by R. So we are getting our answer as option B. I hope you understand.